All right. All right. Good evening, everyone. So this is week 8, and uh, thanks Krishna Kumar for joining. So in this week, what we saw during the lectures was about three-spool turbofan engine and its performance, and also mixed flow turbofan engine. These are the main things that we saw. Uh, and also additionally some different turbofan configurations we saw. So today's problem is going to be related to that. It will be mostly three-spool turbofan engine, and we will study the effect of certain parameters, uh, which we actually didn't go through in detail during the lecture. Okay, so probably more students will join soon. Maybe we will get started. Or anyway, this lecture also will be recorded and posted. You can go through the YouTube recordings after this class. And then if you have any questions, you can come back later. Again, the next week, I will be here from 7 to 9. You can come back later and you can ask me any questions if you have. So without further delay, let me quickly get started. So as I said, uh, three-spool turbofan engine is going to be the focus of this session particularly. We all know why we moved on to three-spool turbofan engine. So we had geared turbofan engines. We want to reduce the uh, rotational speed of the fan, uh, is because there will be aerodynamic losses. So that's why we put a gearbox, and while adding gearbox, we add some efficiency problems. So instead, we and going forward with a very high bypass ratio, very big bypass ratios, it will be even more challenging. So that's why we went with three-spool turbofan. But it is, the construction is a little bit complex because we have three turbines, and the turbine is connected. The low pressure turbine is directly connected to the fan, and it is and even three spools like it's these are concentric spools, right? So making such a component and then fitting it inside is engineering wise it's more complex, but still people have done that. A lot of you know companies have done that. So that is what we are going to study today. Mostly we will focus on thermodynamic cycle of this three-spool turbofan engine. So we know we have fan, which is run by low pressure turbine, and then we have low pressure compressor, or here it is intermediate pressure compressor or booster compressor, you can say, which is run by intermediate pressure turbine, and you have high pressure compressor run by high pressure turbine. And then in between this high pressure compressor and turbine, you have a combustion chamber, and after low pressure turbine you have nozzle where expansion happens, hot gases expands to high velocity, thrust is getting generated. Similarly in the fan again you have uh, nozzle and the bypass stream going to produce thrust. So let's just quickly take a look into the TS diagram. Initially from infinity to 2 there is a uh, pressure rise from P infinity to P02 because of intake, and then from 2 to 3 you have fan, where there is again a pressure rise and temperature rise, and from 3 to 4 you have now this enters into the core stream. So in the core stream you have intermediate pressure compressor, which is between 3 and 4, and then comes the high pressure compressor, where you will reach P5. Okay, and then you have combustion chamber where you are adding heat, and so you will have highest temperature T6. So this will T06 would be the highest temperature, and that will be the turbine entry temperature at this stage. So high pressure turbine is the next component that we have after combustion chamber from 6 to 7, where you see some expansion of gases, and while doing so you extract work, which is driving the high pressure compressor. And then you have 7 to 8, you have intermediate pressure turbine, which is extracting work from the flow gas, uh, and it is driving the intermediate pressure compressor. And from 8 to 9 you have low pressure turbine, which is driving the fan. From 9 to 10 you have tailpipe, there might be some pressure losses. And from 10 to 11 you have expansion nozzle, which is a turbine uh, nozzle. And what you also have is from fan to nozzle you have 3 to 12 you have fan nozzle, where you have expansion happening. So these are the main this is the TS diagram for this 3-spool turbofan engine. So this is a problem I have today. So this problem we have already solved during the lectures. Only thing is we solved it for a percentage air bleed of 10%. Okay. So if you look at here, I have taken 20%. In fact, I will also take uh, 5, 15. I will vary this air bleed and then show how these things are going to affect the performance parameters such as thrust efficiency, exit velocity, and TSFC. So that is the main goal for this session today. So we have 3-spool turbofan engine and with bleeding, and that bleeding percentage we are going to vary and see how the performance varies. So for this 3-spool turbofan engine, it is flying at Mach 0.83 with a T infinity of 216.65 Kelvin and the pressure of 22.632 kilopascal. And the fan pressure ratio is 1.5, intermediate pressure compressor pressure ratio is 5.2, high pressure compressor ratio is 4.8, and bypass ratio is 8.5. Turbine inlet temperature is 1600 Kelvin. Total pressure losses in combustion chamber is 3% and tailpipe it is 2%. So we have pressure losses both in combustion chamber and tailpipe. The air bleeding is given in percentage. It's nothing but 20 percentage of the uh, core mass flow rate at 1.3 pressure ratio from HPC inlet, which means from the high pressure compressor inlet. When the pressure reaches 1.3, there will be some few stages, 1 or 2 stages. After that, we are removing some 20% of the core air, and then we are letting remaining 80% of the core air to expand further in the high pressure compressor. So that is the meaning of this statement. And then we have fuel heating value to be 43,000 kilojoules per kg. An engine mass flow rate is 550 kilogram per second. Please note that this is a total engine mass flow rate. It's not separately core or bypass. It's a total engine mass flow rate. What you have to find is while calculating, let's say the thrust and TSFC, you may need to find the mass flow rate of core. And to find the mass flow rate of core, you need to use this engine mass flow rate information and also the bypass ratio information to arrive at core mass flow rate. Okay. Now we need to estimate the engine exit velocity from core and fan nozzle, thrust, TSFC, thermal efficiency, propulsive efficiency, overall efficiency for different percentage of air bleed, 5%, 15%, etc. All these are, all these we are taking it out from 1.3 pressure ratio from the HPC inlet. Okay, at 1.3 pressure ratio from HPC inlet. So these are the given important parameters for this engine, and these are the efficiencies and losses provided. Give me a second. Yeah. Okay. So these are the efficiencies and losses provided. Now let's go forward and see how to solve this. Before that, we have uh, before that we already have solved this for 10% in our lectures. So for that, these are the performance parameters that we obtained. Okay. So you can revisit the lectures. You can you also have lecture notes available. You can quickly take a look at it. So we for 10% I believe the thrust was 79.68 kilonewton and the TSFC was 22.5. Okay, and the pressure ratios are 82 sorry, the efficiencies are propulsive efficiency is 82.52 percentage, thermal efficiency is 30 percentage, and the overall efficiency is around 25.4 percentage. Okay, and we have velocities and area of the nozzle both for core and fan nozzle. Okay, Now we need to find the similar parameters for 20% air blade. That is the task that we have today. So we can see what are the important parameters that we need to calculate in order to obtain this. So initially we have inlet. From inlet you have pressure and temperatures you can find, and then you have fan. Now from fan, the flow gets divided into core and bypass stream. In the core you have IP compressor, and we have compressor pressure ratios. From there you can find pressure and temperature at the exit of the IP compressor. And then you have HP compressor, whose pressure ratio is also we know, which was 4.8, and from there you can find exit pressure and temperature of the compressor. Also there is a air bleed at 1.3 pressure ratio here. So for that, from this information you can find the pressure and temperature of the air which is taken out of the compressor. And then you have combustor, and the combustor, we know the uh, exit turbine entry temperature or the exit temperature of the combustor. From there you can find the fuel air ratio. And then you have HP turbine, which runs the HP compressor. Using the work energy balance you can find pressure and temperature at the exit of the HP turbine. And then you have IP turbine, which similarly runs the IP compressor. From there you can find pressure and temperature at the exit of the IP turbine, which is P08 and T08. Then you have LP turbine. From there you can find pressure and temperature at the exit of the LP turbine. Okay, by using the work balance between LP turbine and the fan. Now we have tailpipe with some losses. Uh, Using that we can find the exit pressure and temperature of the tailpipe. And then you have nozzle, and whether it is chalked or unchalked, based on that you can find pressure, temperature and velocity of the exit of the nozzle. Then you have bypass flow, where from fan the compressed air comes out with P03 and T03 and gets expanded in the fan nozzle. From there you can find pressure, temperature and velocity based on whether the nozzle is chalked or unchalked. You can find pressure, temperature and velocity at the exit of the nozzle. So I think probably these are P12, T12 and V12. So I think there is some mistake, typo here, which I will update it while I post it in the Google Drive. Okay. Now, yeah. So this is same thing. So only thing the difference here is 20% air bleed. So in the lecture we saw 10% air bleed. Here we have 20% air bleed. There is nothing difference. So ideally your calculation remains same until HP compressor, if you see. Okay. So I will just quickly go through each and every component just for the sake of completeness. So first you have inlet. So inlet, you need to find pressure and temperature. We have this isentropic flow relations. So, and also you have diffuser efficiency. So based on that you can substitute these numbers. The diffuser efficiency is around 0.98, and if you substitute these numbers you will get a intake exit pressure of 35.26 kilopascal, which is same as what we got in the lectures also. So there is no difference until HP compressor. So I'm just going to quickly go through uh, because the Mach flow, but because the Mach number, the velocity of the aircraft is also same. And inlet ambient temperatures are also same. So in inlet, and also the pressure ratios across compressor are also same. So until HP compressor there won't be any change in the pressure and temperature. So the temperature at the exit of the intake would be 246.5 Kelvin. Since intake is adiabatic process, we don't have any isentropic flow relations would be suffice to get the exit temperature at the inlet. And the next component that we have is fan, and the fan pressure ratio is 1.5. The inlet pressure is 35.25 kilopascal. So from there you can find the fan pressure ratio. From there you can find the fan exit pressure, which will be 1.5 times the 35.26, which is 52.89 kilopascal. And the temperature we have from isentropic efficiency relation, you can find the temperature ratios. And based from the temperature ratios, you can find the temperature of the exit of the fan, uh, which would be 1.1396 times T02. Now, uh, if you substitute these numbers, you will end up having the temperature at the exit of the fan to be 280.9 Kelvin. Okay. The next component that we have is IP compressor, our intermediate pressure compressor. And for this also we have given pressure ratios, we know how to solve it. So the exit pressure of this IP compressor would be 5.2 times the inlet pressure, which is 52.89 kilopascal. So if you substitute these numbers, you will end up having 275.03 kilopascal. And similarly, we know the isentropic efficiency expression. From there you can find the temperature ratios. So you can find the temperature ratio, and from temperature ratio you can find the temperature at the exit of the IP compressor to be 475.16 Kelvin. Okay. uh, so this is also same. Yeah, up to this nothing changes from our lecture problem. Now we have HP compressor. In the HP compressor, again the pressure ratios are same. So ideally there is no change in terms of pressure and temperature, because these are station properties. These are this doesn't depend on whether the mass flow rate is whether the absolute quantity of mass flow rate doesn't depend on. Okay, so whether we take more mass flow rate or less mass flow rate doesn't matter. If the compressor has a pressure ratio of 4.8, it will pressurize the air to that pressure. Okay, so and also if the compressor has a efficiency of 0.87, it is going to you know increase its temperature from this temperature to that temperature. It doesn't matter whether you are taking the whether what is the amount of air bleed. It's not going to matter. uh, just because changing the air bleed, these station properties are not going to change. So this is what we are seeing here for the HP compressor. Again, the pressure ratio is same as in lecture problem. So we end up having the exit pressure of the HP compressor to be 13.2 bar. Okay, and similarly we all know this relation. From this relation, you can find the temperature ratio to be 1.6499, and based on that you can find the exit temperature of the compressor to be 784 Kelvin. Now uh, now there is a small difference. Now we have air bleed happening. So whether the pressure and temperature of the air bleed will it be same because of the change in the 20%? Again, there is no this is also not going to get affected, because we are going to take the air at 1.3 times the pressure ratio, which was same as the lecture problem, but only the amount of air is changing, the absolute quantity is changing. So this pressure and temperature is not going to depend on the absolute quantity, because pressure and temperatures are intensive properties. So that's what we know from the basic thermodynamics, right? So um, again, similarly, it's at 1.3 times the HPC inlet, which is P04. So P04P would be having a pressure of 357.54 kilopascal. And we have similarly we can also find the temperature. Again, the compressor efficiency is going to remain same, around 87 percentage. So if you substitute these numbers, you will end up having same bleed temperature and pressure, because the location is same in the whether you increase the air bleed or not, the location is going to same where you are taking out of the taking the uh, taking the air out. Okay, all right. So these are the major differences. So till now there is no difference in fact. So the next component that we have is combustor. So for combustor, uh, now if you think about what happened, we have removed 20% of the air which was in the core stream. We have removed 20% out of it. So before we were removing only 10%. Now in the combustor, what we are doing, we are actually the some amount of air with the pressure and temperatures entering the combustor, and it is leaving at, let's say, set temperature, which is uh, 1800 Kelvin at this for this problem. So the amount of fuel that you add in order to heat this quantity to 1800 Kelvin is now will be different because the amount of this quantity which is entering itself is reduced. So the amount of fuel that you need to add, if you think logically, the amount of fuel that you need to add will reduce. Okay. So that's why when you increase the air bleed, the fuel addition, the amount of fuel that you need to add for the same turbine entry temperature, it has to reduce. So if you think logically, let's see what happens if we perform this calculation. Again, the pressure losses are same, 3% pressure losses. So if you do this calculation again, you are going to get same pressure as we got. It's going to be 12.8 bar. Now the temperature at the exit of the combustor we already know. Pressure at the exit of the combustor is also we know. That also didn't change compared with the lecture problem. Now only thing is we need to find fuel air ratio. So for fuel air ratio we have the energy balance where the energy in would be m dot core minus m dot bleed times Cp times T05, which is this part. And then you have additionally you are adding fuel to it, m dot f into eta b into qr. Burner has some efficiency, so there is eta b. And what exists is m dot core plus m dot fuel minus m dot bleed at T06. So what happened is this m dot bleed, what you did was you have increased it from the lecture problem. So that's why ideally, so you can rearrange this equation and you can get something like this. And here you can see 1 minus b. In lecture we used 1 minus 0.1. Now here we use 1 minus 0.2. So this is the only difference. And since this is in negative, you can actually guess. So this fuel air ratio is going to come less. Okay. So that's what our initial hypothesis was also. Ideally, the amount of air which is entering is less. So the amount of fuel that you need to add to increase its temperature to say 1800 Kelvin would be less. So that's what we guessed it. And our guess is right. So which was around fuel air ratio is around 0.0276, which is less than 0.031, which what we got when we have bleed of 10%. All right, let's go forward with the next component that we have is HP turbine. Now, again, if you think about it, what we have is we have some HP compressor. The HP turbine has to drive the HP compressor. Now, if you think this turbine is a work extracting device, so it has to extract work and needs to run the HP compressor. From the HP compressor side, uh, it is doing some work, but uh, the amount of work required by the HP compressor now would be different because our bleed air has changed. Okay, so let's see how does that affect. So here what we have is this left hand side that we have here is the amount of work that we generate from the HP turbine, and this should be able to drive the HP compressor. And in the HP compressor what we did is, so for some regions, so initially from T04 to T04B, the entire core stream is compressed, and after that we took the some bleed out, right? So after that the lesser mass flow rate is going to get compressed in the from T04B to T05. So that's why we see two different two separate uh, terms in the right hand side. This is the work done or work required by the HP compressor. This is work done by the HP turbine. Okay, so this is the major difference. Only thing is the bleed ratio has changed. Now you can simply think about it. What happens? Again, the mass flow rate on which the HP turbine operates is now lesser, because in lecture we saw 10% bleed air ratio. Here we have 20% bleed air ratio, right? So we took 20% of the m dot core. So the amount of mass flow rate or amount of gas, the quantity of gas that HP turbine operates is lesser. So it has to if it so but it has to give the same amount of work to the HP compressor. So let's go forward and try to think what happens. So if you rearrange this energy balance, you will end up having this relation which is same as what we used in the lectures also. Now only thing is, again as I said, Here the bleed air ratio is 0.1, here it's 0.2. Otherwise the fuel is also reduced because same, we are heating only less amount of air. All right, so if you substitute these numbers, you will end up having temperature of 1538.8 Kelvin, which is less than 1543.57 Kelvin. This is because, as I said, uh, we are operating at less amount of air, and we have to run the HP compressor, where again there has been, for some time there's been full m dot core is being compressed, and for some time there is a less amount of m dot core is compressed, and also your fuel input is less, so your mass flow rate on which the HP turbine operates is less, so that effect has overcome the HP compressor effect. And so that's why you see the amount of work it has to extract more, and hence the temperature and pressure has to go down. So let's see, so now we calculated the temperature. Now let's say our hypothesis, our pressure should go down. Let's see what happens in pressure. So uh, the turbine efficiency is same, and now the temperatures are a little bit different. Now let's see what happens. So if you substitute these numbers here, so you can see here it is 1543 Kelvin, here it is 1538 Kelvin, and otherwise everything is same. And if you substitute, you have a pressure ratio of 4752, however here it is 482, and hence if you do this calculation, you will end up having a lower pressure because it has to take a lot of work. And the reason to take a lot of work is the work wise it might be same, but the amount of mass flow rate has reduced, so uh, it has to expand it to a lower pressure and temperature in order to satisfy the same work. Okay, so that's why you saw lower pressure, and by now you must have guessed what happens to the subsequent components, right? So this is the HP turbine. Now let's see about IP turbine. Again, the inlet pressure and temperatures are already reduced, so by default I would expect in the exit pressures and temperatures compared to our lecture problem should also be reduced. So the turbine efficiencies are same, the fuel air ratio has reduced, so the equation wise there is no change, it's just the work balance. You can see 1 plus F minus B because that is the mass flow rate which IP turbine operates. And on the other side you have the low pressure compressor, and this work has not changed from the lecture, so you can see T04 and T03 doesn't change. So the amount of work I require from the compressor is same, but the amount of mass flow rate entering the IP turbine from which the work is extracted has reduced. So this is going to directly uh, reduce your temperature and pressure to a very greater extent. So let's see what happens. So if you substitute these numbers, you can see the T04 and T03 there is no change. However, there is fuel air ratio change, and then there is the T07 change. Already these are already reduced, so this is going to lead to a lower temperature, which is 1340 Kelvin. However, what we got was for 10% air bleed is 1367 Kelvin. So around like 17 Kelvin difference. Before it was like a few 6 or 7 Kelvin difference. Now 17 Kelvin difference. So as we go further, it's going to get lot and lot worse that you can feel. So the next thing is LP turbine. I mean IP turbine. Again, we need to find the pressure. Let's see what happens. The equation wise, there's nothing changed. Only the numbers would be changed now. So the pressure ratio has reduced as we guessed. It was 0.5195. Now, if you substitute these numbers, you will end up having pressure at the exit of the IP turbine to be 316 kilopascal, which is lesser than 347 kilopascal. All right. I hope until now there is no problem in understanding. The next thing is LP turbine. Again, our inlet pressure and temperature has changed compared to the lecture. Now, again the same argument you can see for the LP compressor. There is no change because the entire core mass flow rate is going to get compressed so to that level. But the amount of mass flow rate that LP turbine operates is lesser. So that is going to again tremendously reduce your temperature and uh, pressure, which is what you are going to see. So the work done by fan is this much with some mechanical efficiency. Here we are taking it to be 99%. There's something to note. And then you have work done by the LP compressor. Sorry, I think this has been changed. So this should be LP turbine. Okay, yeah, this is fine. I think this has to be different. Anyway, I will update this minor change. I think there's some typo here and here. So here it's actually mechanical efficiency times work done by LP turbine is equal to work done by fan. So this has to come here and this has to go here. Anyway, so equation wise there's no change, and if you substitute these numbers, it's going to lead to a lower temperature, which is around 1006 Kelvin. However, your LP turbine exit temperature for 10% air blade was 1070 Kelvin. Okay. Now let's try to find out the pressure. So again, you all know. I mean, I no need to say. I need to explain this equation. We all know what is this. I will just calculate the exit pressure. So your exit pressure, as we said, it has reduced to 80.35 kilopascal compared to 108.17 kilopascal. Okay. All right. And then you have tailpipe where 2% pressure loss, which is also worsening in the situation. From 106 kilopascal at the exit of the tailpipe, you have only 78.75 kilopascal. However, the temperature at the exit will not be different because it's an adiabatic process. Let's go forward. Nozzle, for nozzle again, you can look at it. For turbine nozzle, uh, if you want to get a higher velocity at the exit, you should have high enthalpy gases to the inlet of the nozzle. And now because of our increase in air blade, we already have this already led to a lower enthalpy gas. You can see the temperature is around 106.1 Kelvin. However, for the 10% air blade, it was 170 Kelvin, right? So this is going to obviously lead to a lower velocity at the exit of the nozzle, which is going to affect our thrust. So let's see how our thrust is also getting affected. So as a usual procedure, we have to find whether the nozzle is chocked or not. So you can find the pressure ratios. There could be some time. So for this, in our lectures, when we took 10% air blade, this turbine nozzle was chocked. Now, since our air blade has reduced, our enthalpy at the inlet to the nozzle also reduced. There could be uh, a situation where it may not get chocked. Okay, so there might be such situation. Let's see what happens here. So here, the critical pressure comes out to be 21.526 kilopascal, which is fairly greater than P infinity, which is 22.632 kilopascal. So still the nozzle is chocked. Okay, so there's no problem. But the exit pressure has reduced from 55.89 kilopascal. Now we have only 41.526 kilopascal. That is the problem that we have. I mean, I would not say problem, but reduced pressure. Okay, and you can find temperature ratio. Since the nozzle is chocked, it's going to be simply the temperature ratio is not going to change. However, the absolute value of temperature will change because inlet temperature is different. So you can find the temperature at the exit of the nozzle to be 874.85 Kelvin, which was 930 Kelvin when there is 10% air weight. Okay, that's a tremendous reduction in temperature. Let's see how much that does contribute to the reduction in velocity. So if you substitute these numbers, you will end up having velocity of 571.32 meters per second, whereas previously you have 589. So around like 18 meters per second, there is a reduction in velocity. Okay. Now let's look at bypass flow. In the bypass flow, there is nothing changed, right? So the bleed is the amount of bleed is going to affect your core stream. In your bypass stream, there is nothing, there is no change, right? There is the fan nozzle, and the amount of mass flow rate is same, like we saw in the lecture also. Okay, so in that way I would not expect any difference in the pressure and temperatures. So you can initially, first you need to check the choking condition, and in the choking condition you can see that it is around the pressure ratio is around 1.964. Okay, and which was same as before, because efficiency, nozzle efficiency, and the specific heat ratios are not different. So this, it's not a surprise anyway. So if you substitute, if you try to find the critical pressure, it is going to be 26.92 kilopascal, which is greater than 22.63 2 kilopascal, which is what we got also. uh, and hence we can say nozzle is chocked, and hence the pressure at the exit of the fan nozzle is same. Okay, it's 26.92 kilopascal, which is equal to critical pressure. Now let's find out the temperature ratio. Again, it's not going to be different, so you can substitute these numbers and you can check for yourself. The nozzle exit temperature is going to be same, 234.08 Kelvin. And similarly, you can find the fan exhaust velocity, fan nozzle exhaust velocity, which is also going to be same, because there's no change in the uh, bypass stream. Okay, only the core stream we are taking some amount of mass flow rate. Let's see what happens with the area of the nozzle. So again, for the bypass stream, if you see there is no change, so I would expect the bypass stream nozzle area to be same. uh, However, for turbine nozzle or for the core engine nozzle, what we have is we have our velocity has reduced. So if our velocity has reduced, what happens? The area is going to increase, right? Because velocity is in the denominator. Also our pressure has reduced. So if our pressure has reduced, our density is going to reduce, right? P is equal to rho RT. So ideal gas. So if your pressure increases, density increases. If your pressure decreases, density is going to decrease. So both P and rho and V is going to reduce. So this is going to lead to increase in A level. However, if you see the F also has reduced, because we were our fuel air ratio has reduced because we are operating on a less mass flow rate, right? But how much of that effect is going to counteract this increase in rho and V is we will see. So this is a two effect, but uh, that is a minor effect. Okay, so if you substitute these numbers, you will end up having area of 5071 meter square, which is higher than 0.437 meter square. So this rho and V increase is having major effect. Okay, and also as a whole, the mass flow rate has reduced through the nozzle. That is also the reason. Okay, then we have bypass flow. There is no change in the bypass flow. uh, and you can substitute these numbers. It's going to be exactly same as we got in the lecture. It's going to be 4.002 meters per. So as a engine size, there's not much of a change. Because our bleed ratio has changed. Our core engine nozzle has different dimensions, uh, and hence the station properties have different dimensions, or sorry, different numbers. Let's see what happens to the thrust. So we have to be a little careful while calculating thrust, because thrust also includes the bleed ratio. So basically what happened was, since we took the bleed out, uh, that is going to be used for the aircraft, right? For cabin to regulate the air pressure, for various reasons. It is used inside the aircraft. So it is not really coming out. Okay. So uh, only the thrust is directly proportional to the mass flow rate of the air. So if you are not letting some of the mass flow rate to go out, what happens is that is going to eventually lead to decrease in thrust. So that is one reason. The other reason is our V11 exit velocity also has decreased. So these are the two reasons why we should have, you know, uh, a lesser thrust. On top of it, our exit pressure also has decreased, so that is also going to lead to a decrease in thrust. However, our exit area has increased, so this increase and decrease, there might be some uh, you know mismatch in between them, but the more stronger effect is m dot core has decreased. Okay, or the m dot exit has decreased. That is the main thing. M dot exit has decreased, and v exit also has decreased for at least in the core region. But in the bypass there is no change. So if you go to a very high bypass ratio, let's say turbofan engine, and if you try to change the bleed, there's not going to be much of change in the thrust, because most of the thrust, almost like 70 to 80% of the thrust, is given by the bypass stream. So here you can see the bypass ratio is around 8.5. If you go, let's say 8.5 is also very good, you know uh, fraction compared to core. So changing a small thing inside a core is not going to change our thrust to a very high value. So that's what you will see here also. So uh, the appropriate changes in the uh, values that you need to do. For example, there is a change in velocity, there's a change in pressure. However, this turbine, it's same. There's a change in area. So if you substitute these numbers, you will end up having a thrust of 70.39369 kilonewton net thrust, which was 79.682 kilonewton. So changing a 20% air blade will lead to uh, a 9 kilonewton reduction in thrust. So if you go to a very high bypass ratio engine, so this reduction would be even lesser. So in that way, we don't need to worry much about it. Okay. Now we have TSFC. So as we know, our it's straightforward. Our fuel has reduced, so our TSFC should we should expect it to reduce. But what happened is some interesting thing happened. We got 22.7 grams per kilonewton second. However, for 10% air bleed, you had only 22.5 grams per kilonewton second. So there might be a question, why the fuel air ratio, the F has already reduced, right? So F has reduced from 0.031 to 0.0276. How come there is a uh, increase in TSFC? That is due to the reduction in thrust. So reduction in thrust has taken over the uh, reduction in the fuel air ratio. That is the reason. So these are two competing effects. So if you look at let's say if I instead of going from directly from 10 to 20, let's say if I slowly vary the bleed ratio, let's say from 5% to 25%, if I slowly vary it, there's going to be some point where it will be minimum TSFC, and it is going to increase again. So we will see that it will be an interesting plot to look at it. So before that, we will try to calculate the efficiency. So first is propulsive efficiency, and the equation is same. We have been studying it for last 7 weeks, so I don't need to explain this. So you can substitute these numbers. Only thing is this bleed ratio you need to take into account, because the these two uh, you know uh, terms are, what is the kinetic energy that we are losing at the exit of the engine, right? So this second term is the kinetic energy we are losing at the exit of the core stream, and this is kinetic energy we are losing at the exit of the bypass stream. So what exiting the engine is should be lesser because we took some air bleed. Okay, so those numbers you need to take into account. So and then if you find out, it will be around propulsive efficiency will be around 83.15 percentage, which is higher than 82.52 percentage. This is as expected because our exit velocities have decreased, right? So the and if you reduce the exit velocity of the core stream, you are expected to have increase in propulsive efficiency. Then you have thermal efficiency, and the thermal efficiency is around 30.31 percentage, whereas it was around 30.79 percentage for the that 10% average. Okay, so there is a reduction in thermal efficiency. As I said, the amount of thrust we generated, the reduction in thrust we obtained was more compared to the reduction in fuel efficiency, right? Or fuel consumption. So that's why we saw increase in TSFC also. Again, we are seeing increase in thermal efficiency also. Okay. And then finally, we have overall efficiency, and that is going to be around 25.21 percentage, which is slightly less than the 25.4 percentage for 10% output. Okay. All right. I hope till now there is no questions. It's the same thing. I just changed the air blade ratio from zero point 0.1 to zero point 0.2 and redid the calculations. Okay. So finally, if you see in this table, you can see for air bleed ratio of zero point 0.1, we got this these numbers, and for zero point 0.2 we have a different set of numbers. So we saw around 0.1 or 0.2 percentage reduction in velocity. There is a 16% increase in the exit area of the nozzle, and there is a 7% decrease in the thrust, and some point or 1% decrease in the TSFC. So you can see there is this 8%, around 7 to 8% decrease in thrust because of augmentative effect of both mass flow rate and exit velocity. So even though the exit velocity hasn't changed much, even though the exit velocity reduction is very less, as I said, the mass flow rate is thrust is a linear function of mass flow rate. So if you increase the if you reduce the mass flow rate because of increase in air bleed percentage, it's going to have very detrimental effect in the thrust, and that is what you are seeing it here. Okay. All right. So let's take one step further and let's evaluate how this thrust varies for different air bleed ratio. Okay. So um, as we discussed till now, so I try to repeat this calculation from 5 to 20%. We did 10% in lectures, we did 20% in this session now, and what I did is I tried to do calculation from 5 to 20 in variable steps, and this is how your thrust profile looks. And you can also you can observe certain things here. Okay. For example, if you look at thrust in the bypass stream or T code, this blue line, there is no change in the thrust. Okay. You can see it is just a straight line, which was around like 48 kilonewton. Okay. Um, that is not changing because of air bleed as expected, because there is no change in the bypass stream. What we see is there's only change in the core stream. So that's why uh, when you increase the air bleed, your mass flow rate at the exit is continuously reducing, and the thrust is a direct function of the mass flow rate. So if you increasing linear increase in air bleed causes almost linear decrease in the thrust. So that's what you see here. Okay. And hence the total thrust, which is a summation of hot and cold, is going to be like this. So the next is TSFC. Think about it. What will happen to TSFC? I think I already gave you an idea of what will happen to TSFC. So you get something like this. Okay. So upon increase in air bleed, what we saw is there is some reduction in TSFC to a certain value, and then there is a tremendous increase in the TSFC after a certain value. So there is some optimal lower minima in your system. Okay. Which is due to, because of increase in air bleed, your fuel consumption will continuously decrease, because you no need to add more fuel to heat the value to 1800 Kelvin, right? So if your mass flow rate itself is lower, you need to add only less fuel to heat that. So uh, that's the reason your fuel uh, air ratio continuously decreases, and but during that what happens, the thrust also decreases. So there is a competition between F and T, which is on numerator and denominator of TSFC, which is causing this trend. Okay. All right. I hope this is also clear. That's why we see what do you call a non-linear trend here. Okay. The next is efficiency. Uh, So okay, before that we have velocity. And as we expected, the fan nozzle it's going to remain same. There is no change in the bypass stream, but in the turbine nozzle, what we have is from around 595 meters per second, it is continuously reducing and reaching 575 meters per second at 20% air blade. Okay, so which is also expected because our enthalpy to the inlet of the nozzle it's going to continuously decrease because our amount of mass uh, the um, amount of mass of gases that these turbine stages, HP turbine, LP turbine, and the IP turbine is going to operate is as reduced on increasing the air blade. So your enthalpy amount of enthalpy extraction from these gases is going to be more, and hence the enthalpy at the inlet of your nozzle is going to be less, and because of that you have such a reduction in velocity. Okay, now look at the efficiency. So uh, we have a continuous increase in propulsive efficiency and a continuous decrease in the thermal efficiency. Yeah, and then thermal efficiency and overall efficiency is not that much of a difference. It's almost a straight line, but propulsive efficiency slightly increases because of air blade, and this is due to the velocity of it. Exit velocity of the turbine nozzle is continuously decreasing, and that is leading to an increase in the propulsive efficiency. Okay, so that's the idea that I want to give. If you are increasing the air blade from 5% to 20%, what are all the expected changes that you would see in terms of different parameters, including performance parameters and also the station properties, pressure and temperature, in a three-spool turbofan engine. Okay. I hope this would be helpful for you to understand the concepts also. And if you have any questions, you can ask me now. Yeah. So that is a question that I have today. I think we addressed all the things. We estimated the exit velocities of core and fan nozzle, thrust, TSFC, thermal efficiency, propulsive efficiency, and overall efficiency for different air blade. Okay. All right. So if you have any questions, you feel free to ask now. Uh, if you, if not, we can meet next week 9. Okay. We'll meet and discuss probably a new problem. Okay. So there has been few typos uh, in the slides. So what I would do is I will update those typos, and then uh, I will upload it in the drive for your references. Okay, I guess that is not a typo. I guess it is because I'm viewing it in PowerPoint here. Probably there is some change during updates. That's the reason, I guess. All right. Anyway, thanks for attending. And then we will close this session here. I will be available here till for another 1 hour. If you have any questions, you can ask. If not, we will meet next week. Okay. Thank you very much.